You're always the first one here, Finn.
I know. It's because I'm good. I
Yeah.
always join like 5 minutes early because I have really nothing else to do.
Uh, what? You don't have anywhere to go? Nothing to do?
Well, I mean, I wake up like 10 minutes before class starts with the sole purpose of getting first to class.
Sure. Sounds good. That's dedication.
Yeah. How are you doing, Dr. Schmidt?
Okay, I guess. This is getting pretty old.
Yeah, already.
I thought people were sort of focused for the
Hi
first couple of weeks,
guys.
but
Good
it's just
morning.
good morning, Anita.
Let's go
Uh,
get some breakfast.
yeah, I expect that
I
the
needed.
novelty of this method wears out. People will get more and more fed up with it.
I saw your email, Dr. Schmidt. Are you
Yeah.
asking about what science I'm gonna take?
Yeah. What science are you going to take next year?
I talked to my parents. I wanted to take AP Chem,
Okay.
but like I don't know. And I want to take AP Physics C, but then I know how hard it will be. So
You're in Calc now, right?
yeah, I'm gonna go to BC next year,
Okay.
so I can take that
I think in some ways C might be easier.
because it's more algebra based.
Yeah.
Yeah.
There's a lot more like math calculations and stuff.
It's like less understanding and like more calculation.
More,
Yeah,
can you find the right equation and manipulate it?
that's so true. So yeah, I talked to my parents about it and they were like, if it's more calculation based, you should go take it. But we never know. Yeah, I'm just gonna see how it goes next year. Because I want to take that class. It seems really fun.
Okay. Sure.
Yeah. What about you teaching here?
Your honors chem person will mostly recommend you for AP Chem, but I assume you're doing okay there.
I'm hanging in there.
Okay.
You know, like my chem grades is even worse than my physics grades. But
Uh,
yeah, because I did not try hard in that class. Like, I don't know. Yeah, so yeah, I'll work harder this trimester and hopefully I'll be qualified to take AP Chem. But if that doesn't work out, like honors bio is good too.
well, I think you need to take honors bio.
Eventually in my senior year, probably.
Yeah, but I don't know why you wouldn't do it next year.
I don't know, because I want to have a chill senior year.
Oh, there's no such thing. Right, Fan? Just as soon as you think that there's a chill senior year,
There's
they
not
come, the world comes and takes away your entire senior spring.
Exactly. Exactly.
Let's confuse the
It
seniors
just
with graduation.
doesn't work.
It does not work out well. So I don't really know. I'll reply your email later. I have to talk to my parents or like
Well, I don't know how this really works in terms of like other classes.
yeah. I don't know. I think I'll take like English, US history, science, like two sciences. What else?
Okay.
Math. So like
Yeah.
five.
There you go. Well, it's just an initial recommendation. I don't think you're locked into it. So I'll
So,
recommend you though for those two classes.
thank you. Is it like okay, yeah, so you recommend me with classes and I'll like it's like my decision to like follow your recommendation or not.
Your advisor.
Oh, my advisor.
Yeah.
What will you teach next year? Will you still teach AP Physics too?
I don't know. I have no idea. AP Physics 2 isn't being offered. Um,
Yeah, it's A1, isn't it?
AP Physics 1 will be offered. I don't know what I'm going to teach next year.
You should teach
Because
AP Physics C, okay? Please. There should be like 2 physicsy classes.
Yeah, I don't know. We'll see.
Hi, Mike.
I don't like the calculations as much. I
Oh,
find it
much
kind of
prefer
boring.
calculations. Much prefer calculations.
I know.
Hello, Dr. Schmidt.
Oh, mix up nice and late. Man, that seems a little slow today.
Yeah.
Is that happening to everybody or just me?
It's everyone. Or it's me too.
I was a little worried that the internet might break with everybody working from home, but it seems to be holding up okay.
Yeah. The first few days it broke for me. Cox just didn't have enough
Yeah.
internet.
Plus, it's designed at homes to be mostly receptive to data and not to pump data out the other way. So that can be a problem too. I'm just hoping that Luke is trying to connect, but he's hanging.
I imagine he's sleeping.
Oh, well, his computer's trying to connect. Maybe he set it up automatically to connect for him. Have you ever seen an old claymation show, Wallace and Gromit, where Wallace is an inventor?
I said so much.
Yeah, he should invent a thing to appear in his own Zoom calls. We should get to work on that. And the dog knows everything. The dog is the real person who understands everything. Classic. Okay. Well, there's Beanie. All right. So I thought today we would discuss a couple things. First of all, if you are not a senior, most of you are seniors, but if you're not a senior, you got an email from me about class recommendations for next year. Just respond to that whenever you have a chance. It's just the beginning of the process. Of course, there's a lot of back and forth as we sign up for classes. So it's really just the initial recommendation. And if you did fine in this class, then you know, another AP class is probably okay for you. If you struggled a little bit, then you should probably think twice about another AP class. If you are a senior and you're going off to take college, many of you, vast majority of you seem really interested in engineering. So you're probably going to take a calculus-based physics class. It's going to cover a lot of the same topics. But your conceptual understanding will really help a lot with that, believe it or not. And I think you'll be in good shape to take that class. Okay. Any questions about next year science classes that I can answer, given that I don't know the future any better than any of you do? Okay. So a couple things about, I looked briefly through the thermodynamics review. On thermodynamics review number 2, you're supposed to identify and describe the primary process that transfer energy, processes that transfer energy, I think that's a typo there, transfers energy through the wire's electrical insulation, and the primary process that transfers energy through the water. There's 3 main types of thermal energy transfer: conduction, convection, and radiation. Okay, so conduction is when hot particles, so remember, hot means fast moving. Temperature is a measurement of the average kinetic energy in a particle. So fast moving particles are directly touching colder, slower moving particles. And then they collide together. And as a result of that collision, the fast moving particles end up moving slower, and the slow moving particles end up moving faster. So at a big macro level, if you have 2 objects, here I've got my calculator here and my brush for when my cat jumps in my lap and I need if the calculator is really hot, okay, then and it's touching the brush, then conduction at the parts where it's touching, conduction will make the hot particles in the calculator, the fast moving particles, those will smash into the cold moving particles in the brush, and then the brush will get hotter because the result of those collisions is to make the particles in the brush move faster. Okay, so on a macro level, thermal energy transfers from hot objects to cold objects, transfers via contact from hot objects to cold objects. And the reason it goes from hot to cold has to do with the second law of thermodynamics, as we discussed last class. All right, any questions about that? Yeah, Anita?
So for conduction, is it the 2 objects has to be directly touching? So
Yep.
does that mean like solid to solid, liquid to solid?
Yeah.
Like you specify the classification for that?
It's usually used for solid to solid. Let me see what they said. I don't love these, actually. I think they're actually poor descriptions of what's going on and a little bit artificial. Like there's nothing really different about a liquid or a solid touching, and they should both conduct.
Yeah.
Let me. So it's usually solid to solid.
So liquid to solid would be Convection.
Yeah. So convection is when hot particles, so hot, fast-moving particles, collide. Collide with colder, slower moving air or liquid particles. And then those warmer air liquid particles rise, right? They rise up through the air liquid. So this is how, this creates currents in the air liquid, which distribute the thermal energy throughout the air liquid. Okay, so if you have, you have a water bottle, and then you start heating the water bottle at the bottom, the hot water will start to rise, and it actually starts going like this. Hot air goes up in the middle. I think cold goes down the sides, but it's been a while since I studied that exactly. Okay, so right, the main thing is that convection is the transfer of thermal energy through an air or a gas. I shouldn't say air. I should say gas. Right. Okay, so that is for the transfer of thermal energy throughout a gas or a liquid. So conduction is a slower process than convection. So the main reason that these are actually different, okay, is because here, I should probably try to draw a little bit. If you have a sample of a particle, right? So if I have two solids touching each other, and these are hot particles over here next to the sample, okay? When they hit the colder particles, right, the red particle here will actually physically hit the blue particle. And then that'll make the blue particle start to move faster. So it'll become a little bit faster moving. Okay, and then the green particle then hits the next blue particle in turn, and then it starts getting faster. And then it hits the next one in turn, and then it starts getting faster. So the particles themselves don't move. They transfer energy by shoving the next particle in line. Right? But with convection, energy is transferred like this. You have a bunch of cold particles in a gas or liquid, so they fill up the whole container. And then you have a hot particle down here at the bottom. And then that hot particle actually physically moves into the top, so it becomes up here. So it's not transferring energy by colliding, really. It's physically moving to a different spot, and so therefore the average kinetic energy up here is higher because a new particle joined that was faster moving. Okay, so the particles themselves are actually physically moving, whereas with conduction, they're transferring energy via collisions. But of course, both are happening in convection. Of course, there is some collision going on and some transfer that way as well. All right, clear as mud. Questions about that?
Why would it be slower than convection?
Why is conduction slower than convection?
Yes.
Because the physical movement of particles through a fluid is faster than having to collide with everybody. So if we were in class, I might have you all line up in a line, all right? And then have everybody high five the next person in line and see how long it takes to get the high five all the way down the line. It'll take a little while, right? But if somebody just starts at one end of the line and walks to the other end of the line, they're going to do it faster. Okay, so it's not the actual transfer of energy from the source that's faster, it's the distribution of energy throughout the sample that's faster. Does that make sense? Because this actual source, like your burner here, is putting energy into the bottom through conduction.
Okay. Yeah.
All right, radiation is the transfer of energy through electromagnetic waves. Okay, so this is why, you know, the sun warms us up. Okay, so i.e. the sun warms up the earth this way. So a particle can be hit by an EM wave, and then that particle can start to move faster. All right, so if you have a pet reptile, we had turtles for a really long time. The thing you should know about turtles is that they live forever. All right, so we had turtles for like 14 years, and that was enough. I was tired of cleaning turtle tank. So when we moved from here from Pennsylvania, we found a home with this person liked to collect all sorts of animals, tanks and stuff, and we left the turtles there with that person. So, but if you do have any sort of reptile, you need to put an infrared lamp or some sort of lamp in their cage. And that lamp will heat up the cage with radiation.
So like radiation does not happen only in vacuum, but also just in like air.
So technically speaking, right now, you're getting a little bit of thermal radiation from the light bulb above your head. Okay, it's not that noticeable, but it's there. All right, so if you if you have a campfire, the convection will mostly send heat up into the air. Okay, and the conduction is pretty slow. And so when you're standing next to the campfire, most of the energy that you're getting is from radiation from the campfire. Right, a lot of it anyway. Okay, I think that's more than this topic really deserves. Let's look at thermodynamics review number 2. What do we want to talk about on this one?
Number 1.
I think 2B or 2, just 2 in general.
So I heard 1 vote for number 1 and 1 vote for number 2, which is problematic.
Number one.
Yeah, I vote number 1.
No, not number 1. Not number 1.
Well, I just went over B.
Not number 1.
pretty
I mean, number
thoroughly.
1A. That's what I meant.
So
Yeah,
we'll do
1A.
number 1A for
1A.
like 5 or 10 minutes. Okay. But once you get it, I think it'll be pretty straightforward. So
Yeah, I got number 1A.
I will send you into breakout rooms to discuss, but we won't spend more than 7 minutes on this.
So did you guys? I thought I'm not sure if I figured it out, but you wanted to screen share? That'd be easier. Okay. So there's what we have for the problem. So I took what the power equation was, start off, because we know what our power is with the 10 kilowatts right here. And then I also took the change in voltage equals the current times the resistance, because what we're solving for is the length right over here. So I knew that we needed R in order to get to the length over here. So anyways, I readapted the equation to get R by itself. The change in voltage over the current is equal to the resistance, which is the resistivity times the length over the cross-sectional area. And so then I took what we had, 1,000 watts equals 240 volts times the current.
Isn't that 10,000 watts?
Is it 10,000? Oh, that's great. Well, I'll have to redo that in a second then. So anyway, so 10,000, it'll be one more decimal place then for all the answers. Anyway, so then it would be 10,000 times, or 10,000 divided by 240. Then you just plug in what you had for your I over, say, over here, back over here now to find what the resistance is. And then you can use the resistance that you have, your value, to solve for what L is.
I don't understand. How do you get I again?
So I got I by going with the power equation. So we have power equals the change in voltage times I.
Right.
And so then I got 10,000.
Oh, I see.
I gotta change it to 10,000 and then equals
It'd be
240.
easier to read if you wrote this equation right there.
Yeah. Okay. So
Okay.
I think, I'm not sure if this is right, but this is what I tried to do, I guess.
And then your resistance is this.
Resistance would be, yep, that. Resistance equals the change in voltage over, I'll rewrite the equations next to them. The change in voltage over to I, because we saw, again, like I said, the numbers from this point on are all incorrect. All the numbers are wrong.
Right.
Because I forgot to add one more zero. And I thought I had done it. And then you get your resistance here. And then you can plug that into the resistance equation, being the resistivity times L over the cross-sectional area.
Okay, so it would be easier to read if you would write the power equation here, and then the resistance R is equal to delta V over I here. I think you can just say that because that's a variation of Ohm's law. That's not very deep. And then you'd say things like, note that resistivity also equals cross-sectional area times resistivity. Length times resistivity divided by area here. And then plugging in gets you this. Okay. Writing all your equations over here is a little bit harder to read. Because it's not like there should be an order to your argument. And your order is a little disjointed. Okay, does anybody else have questions about this? Okay. Does anybody have it in a more ordered fashion? Okay. All right, Jonathan, you're probably up to explain it to the whole group then.
Great. Nice. All right, let me redo it. I'll change it up now.
Okay. I'll go visit another breakout room, give you a minute or two.
And 6 ohms.
I'm not sure. I haven't done that yet.
Does somebody have this on their screen or something? Are we all using other devices to connect?
I'm using a different device.
Yeah.
I can share.
Alright, divided by density.
So I started with, we need a power of 10 kilovolts
Mhm.
equals current times change in voltage. Change in voltage equals 240. So we're going to need a current of 41.6 amps. So we're going to need a resistance of 5.76. And I just need the equation for resistance.
It's move your
So you keep moving. It's right there.
Yeah. So length over
cross-sectional area.
So they give us this, and they give us this.
But we can't get
So we just need to figure it
the
out.
density.
It's not the
That's not
density.
density.
It's resistivity.
Oh yeah,
Mhm.
that's my problem. That's what I was doing. Resistance.
So they do give that to you.
Yep. Let's see. Times length. Equals I.
Okay, I'm gonna bring us back to the main room here. All right, but that looks good.
Sounds good.
You ready, Jonathan?
Okay.
Well,
Sure.
there's still a few people stuck in their breakout room.
All right, I'll wait then.
I'll let you know when they all show up. They have 16 more seconds before they're kicked out automatically. Okay. So everybody's here now. Jonathan, you want to show us yours?
Yeah, I'll get it there. Let me get it. All right, here we go. Share. Okay. So I'm gonna move this out of the way. Okay, so to start with this one, we have to find what the variables we have in this equation for. So we're solving for the length, which we know requires this equation. Resistance equals the resistivity times L over the cross-sectional area. So we know that we have to find the resistance, which we can find using Ohm's law and reordering the equation with R equals the change in voltage over I. Then we have to find I using the power equation. So going forwards now, power equals the change in V times I from our equation sheet. So I originally had 1,000, and then Dr. Schmidt pointed out to me, so I just fixed it up just now. So it's 10,000 watts times the change in voltage 240 times I. And then you get 125 over 3 amps. And then you go to the Ohm's law equation. So you have resistance equals the change in V over I. You plug in their 240 again, divided by the 125 over 3, gets you 5.76 ohms. And then you can plug that in to R in this part of the equation, the resistance equation. And so then we also had the resistivity being 3.0 times 10 to the negative 6th times L, which is what we're solving for, over the 1.3 times 10 to the negative 5th meter squared as a cross-sectional area. So we have our we have one variable that we're solving for and 3 others that we already have plugged in. And then once we do all the little math and the calculator stuff, we come out with 25 meters as the length of the heater.
It's pretty long.
It is pretty long.
Yeah, that's
But
what I do. So.
I guess for a swimming pool, you could just go along the bottom there for quite a while. Or I think they often coil it up too. And I don't know how that affects the ultimate efficiency of it. Okay, so that looks good. I really love, Jonathan, how you worked backwards from where you're trying to get. That's an excellent thing to do if you're ever stuck. So you say, well, what if I knew this? Then I could do it. And then you change your target and figure out where to go to from there. All right, if we look some more at C, I feel like we've done problems like C several times. So I don't know. I think I feel like they're very likely to ask a question like C, but I feel like they're less likely to ask a question like, well, I don't know. The nice thing about this whole problem is that it kind of integrates circuits and thermodynamics, which I feel like they're very likely to do. I don't know. It's all a guess. But anyhow, I feel like we've done a lot of questions like C. So I'd like to skip that one unless people object strongly. All right. How about D? Was D pretty straightforward, or was it something that we should go over again? Yeah, we should do this one. Okay. Well, we'll spend a quick amount of time doing D. I'll go into other breakout rooms then. All right, let's do D really quick. All right, somebody want to show what they did on this one?
Sure.
Over this problem before, so we think we got it.
Okay.
Like this, right?
You just use PV equals NRT.
Oh wait, this is 2D.
No,
This is 2.
That's a different thing entirely.
Yeah.
Well, you found the air. This seems pretty straightforward. Why are you doing all this PV calculation? At 202,000 newtons, that is roughly like a door trying to hold up 220,000 kilograms.
I mean,
It would be like if you put a 20,000 kilogram block on the door, like horizontally, and tried to make it hold up that. Did you think the door is capable of holding up that much?
I thought it was a really strong door,
Okay.
bolted and stuff.
But it says, the air pressure inside of Fort Knox is. So I think something's off here.
I mean,
You have a lot of different desperate approaches written down here.
yeah, I mean, so I went with this one, but like I feel like I could have done this one also. PV equals nRT. Actually, wait, no, that wouldn't make any sense. I didn't really know how to write it any differently though. Like, I just used the P V I over T I equals P2 V2 over T2.
So you're finding a new pressure.
Yeah, because it was a new temperature. And I just plugged the Kelvin values, which I think.
So you have a pressure of 112,000 pascals. That seems reasonable, right? It's a little bit more than, no wait, 10 to the fifth is 10,000 pascals, right?
Yes. Yeah.
Yeah.
So why do you have 112,000 pascals here?
I
That's over
cross-multiplied.
10 times more. I know, but it just seems like something's off because you should get 10,000 times 310 over 276. That's not 10 times more.
Wait, 10 to the fifth is 100,000.
Okay. All right,
No.
that's fine. 1, 2, 3, 4. Okay. So yeah, 112,000 makes sense. All right. And then I guess you put it here. Why did you multiply?
Pressure times area equals force. Doesn't it? Because force over area equals pressure.
Yeah. It's true.
Well, what I did is I found the difference in pressures. And because if the door's open and then it's closed, I was thinking that at that time, with that temperature, there wouldn't be any force on the door. And then after the door is closed and the temperature starts increasing, then pressure would be applied to the door from the gas. No, or force would be applied to the door.
Yeah, I guess it is just a lot. I mean, air pressure is actually really strong. And the answer is 20,000 newtons or 200,000 newtons.
I thought it did seem unreasonable, but like I didn't see any other way it wouldn't.
No, that's right.
Because it made kind of sense.
Okay. Yeah, air pressure is, I guess, door. Well, see, the thing is, all right, we'll talk about in the whole class why the door doesn't break. All right.
Because it's spread over the whole
No,
area.
that's not why.
It has pressure on the backside of it too.
Exactly, Connor.
Oh. Okay.
So there's pressure on both sides, squeezing it. So the actual, only the difference in pressure would be causing it to break.
So that would be about double, or basically about.
No, it's only about 310 over 276 bigger.
Oh, okay. Yeah.
So it's only about 12% bigger. It's still going to be significant. The door needs to be pretty strong to do this. Okay, let's head back to the main room here.
Okay.
Luke, you get to explain everything.
Okay.
Let's see.
Okay, everybody's here. So Luke, you want to show us how you did it?
Okay. So basically, I did the PI VI over TI equals P2 V2 over T2 for like that whole thing, that equation, and I just plugged in because I wanted to find the P2 since T, like this is, you know, all the information for the initial state and you just want to find the pressure for the second state. And so when you plug it in, you get 112,318.840 blah, 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 pascals for P2. And you do that pressure equals force over area. So you just multiply the area you got off the door times the pressure, which gives you an enormous amount of pressure.
Enormous amount of force.
Enormous amount of Newton, yeah, force.
So why does that make sense? I mean, that's like we were saying in our group here, that's like putting a 20,000 kilogram mass on top of your door, which like taking your door and making it horizontal and then putting a 20,000 kilogram mass on top of it, which seems like it would break the door.
Like there's like air outside, so it's balanced.
Yeah.
I mean, if in the space, then it's gonna blow up.
Right.
But
So
like
this
we
is why
have pressure on us too.
Yeah, this is why making making a space station is a lot harder. Because in this International Space Station, they have exactly this problem. There's this amount of stress on every single wall.
Wait, so that's why there's the airlock.
Yes.
Oh, that makes so much more sense now.
But so if the air inside the room heated up to this temperature and the air outside stayed at 276, then you would get a difference between the two of about 20,000 newtons, which is about a 2,000 kilogram mass, which is, it needs to be a pretty strong door to withstand that. If you've ever been in a house where the door suddenly swings open or slams shut, right? That's just a very small amount of air pressure difference that's causing that, or the windows shake. Okay, so air pressure can get pretty strong and do a lot of stuff. All right, I thought that was interesting. Any other questions about this? No. Okay. So let's look at problem number 2. Should we do 2? I can't really see all you folks too. Should we just start at number 2 at the beginning?
Can we go over? Can we start at 2A2?
To A2, calculate the temperature of the state and the gas speed. I think like the force is pretty similar to what we just did.
I wasn't sure about the
Okay.
indicate the microscopic property of the gas that is characterized by the temperature.
Oh, somebody answer that? That's kind of that's a short answer.
Does that have to do with like average kinetic energy?
Yeah, that's how fast they're moving.
I mean, Dr. Schmidt, do we need like say that it's moving relatively faster than like room temperature because it's like a lot hotter?
That would be one way of indicating. So let me see. Let me see what it says in the key here. It just says 1 point earned for indicating that temperature characterizes average speed or average kinetic energy. And average is underlined, so I guess they really wanted you to say average.
Okay. It's kind of.
That's kind of arbitrary, in my opinion.
Yeah. The question is so vague. I don't know how to answer this.
Yeah, I would say average kinetic energy is your best answer.
Alrighty.
Okay. All right. Shall we do B then?
Yeah.
All right. All right. We'll head off and do B, and I'll get to the final room here finally. What happened to my breakout rooms? All right. Did you freeze there, Finn? You don't look like your internet's so good right now.
Number. So like, hi, Dr. Schmidt.
Oh.
So we all agreed on one, that the temperature is going to be greater. Because ignore my very bad handwriting. Thank you. So we know that since the number of moles is constant, which means the product of P and V varies directly with the temperature. If we scroll up, we can see that the product of P and V in state A is less than the product of P and V in stage B, which means as it goes from A to B, the temperature rises because P and V is greater. And temperature is characterized by the average kinetic energy, which is also the internal energy. So yeah, that's basically what I said. So the internal energy will become greater. And for question number 2, if we calculate the temperature at stage A and B, I just calculated them out. One comes out to be 240.67, another one comes out to be 300 K. And if we plug in that value for the equation, energy is equal to 3/2 K N KBT. I think I missed an N here, or it's not showing up. But yeah, like here. So it should be, so I got like an amount of 1,478 joules, like the change in internal energy.
You got how much?
1,467.
Why not the 3,000? Sorry, over here you have 3,000.
Oh, I mean like that's for heat or like thermal energy. I was talking about the internal energy. So yeah, but like we have to figure out the internal energy and the work to calculate the thermal energy. So I got 1,400 for the internal energy, and I got a really negative number for work. So I got like negative 3,000 for the thermal energy.
So you got negative 3,000 for the thermal energy.
Yeah.
Let's see. So delta U, shouldn't that be 3/2 kb delta T?
Yeah. Yeah, and the value I got is 1,400 for that. I do not know why my notebook is not syncing at this point, but so yeah. So I got like something like 1,000 for the change in delta U, and then I calculate the work, and the work should be negative because the gas is doing work because it expands.
So here for delta U, you got, what did you get for delta U?
1,478.
All right, how did you find work?
I just multiply the area underneath the shaded area.
And what number did you get for that?
I got like 1.5 times 2.03 times like 4,500 negative.
Okay, so when you're going from A to B to C, then you're going from A to B. So this whole square gives you work.
Yeah.
Okay. And then B to C does no work. So it's not the area of the trapezoid, it's the area of the rectangle.
Okay. So that would be
that's going to be different there.
That's going to be larger. So that will come out to be 6,000.
Yep.
And Q would be 1,478.67 plus 6,000.
Yeah, so like, I don't, your answer is pretty close. They in the key, they round it to 1,500.
1,500?
For delta U.
Oh, for delta U.
So instead of 1,478, they round it to 1,500.
Oh, so the answer would become like 7,500.
Yep.
Okay, yeah, that makes sense.
All right, Kyle and Finn, you were pretty quiet there.
I was taking notes.
Yeah. Did you follow all that?
Yeah.
Questions?
Not really.
Okay. All right, we're gonna head back to the main room then. Anita, this is reasonably difficult to follow, so do your best to clarify it.
No, it's not even syncing. It's really weird, but
Oh, you're changing it, but it's not syncing?
yeah, it's not syncing, so that's
Oh.
super weird.
Huh. That's
It's
weird,
annoying.
because it should like show on your screen directly.
Yeah, because I'm using my iPad to write, but then
Oh, I see.
yeah,
I see what you're saying. Okay.
yeah, it's really
I'll see if it's different on my screen. Maybe I'll share my screen when we get back to the main room.
yeah.
Okay.
Bye.
Okay. No, we're still missing some people. There's always one room that just hangs out. I sort of suspect that they are maybe
Or
doing
wind
other
down.
things.
They want to wind down the clock.
Oh,
Yeah.
wait, look.
Okay,
Yeah.
we got everybody back now.
It's because yeah, I didn't do the change. It was just I just calculated the energy at that point.
All right, Anita's going to show us how to do how she did this. But before she does that,
Yeah.
I forgot to tell you folks about passing with honors. So I'm going to do that really quick. So if you go to the online course expectations, I outlined pass, fail, and pass with honors. Passing is passing. Any grade with a D or higher is passing. And then passing with honors, you must achieve a final numerical grade of greater than 90%. And then I thought you should, I thought a good thing for you to do would be to learn something about unit 6 or 7, since we're not going to cover them this year.
And that's waves and optics.
Optics and modern physics. So waves and optics is unit 6 and modern physics is unit 7.
I'm excited.
So you learned some of the material in unit 6 on light and optics, and unit 7 is modern physics. It's in your textbook. I can point you to the right chapters if you need that. Or Khan Academy or stuff, and then demonstrate your knowledge. So you can either write 2 pages of a textbook on your topic, or you can make a video telling me about your topic, and then you can do 5 problems in your topic area completely. Note that 1 AP style free response question would be acceptable here, because that has at least 4 or 5 sections. So if you can find an AP style question and then do it, that would also be fine.
Dr. Smith, I just have a quick question.
Yeah.
Are we doing anything after the AP exam?
So we have sort of formally requested that we be allowed to let you folks go after that. But that was a request that was passed up the food chain.
Okay. Because I'm thinking I might do this after the AP exam.
Sure.
Same.
That's fine, and I certainly will
Okay.
be around to discuss it.
Okay, that's good.
We have 3 classes after the AP exam, I think. Anyhow.
So
Yeah.
one more question. The AP style, that acts as a substitute for the other 5 problems. You don't need to do one.
Yeah, so you could do like 1 AP style question. So basically our homeworks have been 2 AP style questions every homework assignment. So this is like half of a homework assignment, basically. Okay. I don't think it should be too onerous for you to do this, but I did want to make sure you had to do something a little bit extra just to show that you're, that's what passing with honors means to me. Okay, so Anita's going to tell us about part B here, part B2.
Yeah, this is really messy, but so in order to find the thermal energy, according to the second law of thermodynamics, or the first, heat is the internal energy plus or minus the work. So we can figure out the internal energy by calculating the initial temperature and the final temperature. And the internal energy has an equation of 3/2 NKBT, delta T. So through PV equals to nRT, we can find the temperatures of the initial and final stage, which is temperature at point A and point C. And so I got a value of 1,500 for the change in energy, internal energy. And if we go to the graph above, we can find the area that's underneath the graph as the work. It's not the trapezoid, but the whole thing. It's because the gas has passed to stage B, and there's no work from stage B to stage C. That means the work done is from stage A to stage B. So yeah, that's the total amount of work done. So that's going to give us a value of 6,000 joules. And that is negative because the gas is expanding, so it has done work on the surrounding. So if we write the equation, we can get 1,500 joules is equal to Q minus 7,500, no, is equal to Q minus 6,000. Yeah, so then we can figure out Q, which is equal to 7,500. Yeah, so basically calculate the temperature to figure out the change in internal energy, and then figure out work to get heat or thermal energy.
Okay. All right. So great class. I think our next class is Friday. No, not Friday. Thursday at 8:30. All right, I put up the next homework assignment, which is some electric field stuff. I expect a lot of discussion on that one. All right.
Wait, Anita, wait. What did you write for the Q equals right above the negative 3022 joules? Back down, like.
Oh, yeah, that one is wrong because I figured out the work is wrong for my calculation. So please ignore that. But what is above that is, I'm saying like Q is equal to internal energy, change in internal energy plus the work.
Oh, okay.
Yeah, this one
so
is
that's
equation.
right. But the bottom part is wrong.
The bottom part is wrong.
Okay. And then you figured out the temperatures, and then you.
Yeah, and I used the equation for calculating internal energy, which is 3/2 number of particles times the Boltzmann constant times change in temperature.
Oh, okay. And then you subtracted, or then you added the work done.
Yeah, and then added the work.
Oh, okay.
Does it tell
Okay.
you how many particles there are somewhere?
There are 2
2
moles.
moles.
Oh, 2
yeah.
moles.
Yeah,
Right.
every time they
So there you go. They assume that you know basic chemistry.
Yeah.
Just casually throw that in there with no.
I know.
Hopefully you do know basic chemistry.
Okay.
Thank you, Dr. Schmidt.
Thank you.
Thank you.
Thank you.
Thank you, Dr.
Thank
Schmidt.
you.
Thank you, Dr. Schmidt.
See ya.
See you
Oh,
tomorrow.
wait. What was C? Wait.
Oh, we haven't done C yet.
Oh, what?
I think C is just negative 1,500. I don't know why the negative sign is not showing up on the screen, but it should be negative.
So like, wait, so we just haven't, we're not, should we do it next class or like?
Well, so kinetic energy is just the internal energy, right?
Yes.
So she already found the change of internal energy up here in
Okay.
B2 being 1500. So this should be negative 1500.
Because
Oh.
A2A is 15, so C2A is negative 1,500.
Oh, okay. Oh, that makes way more sense actually.
Because A2A is no change in kinetic energy. So, yeah.
Okay, thank you.
Bye. Have a
Bye.
good day, everyone. Bye.
Goodbye.